Okay, so we're going to do an example here in class 8. I wanted to do for work energy. I wanted to include a spring problem. So we have this 10-pound collar, and it's going to slide without friction, and that's good news, along this horizontal rod. And it's in equilibrium when it's at right here at this location. When it is pushed 5 inches to the right and released, the underformed length of each spring is 12 inches, and the constant of each spring is 1.6 pounds per inch. So we want to find the maximum speed of the collar, and we want to find the maximum acceleration of the collar. So I'm going to draw this thing, try to draw it somewhat neatly here. And here it is, it's a ghost, and I'm going to move it over here so that it has moved all of 5 inches right there, okay? And so we have our spring, it's compressed right here, and here's where the spring is attached. And I'm going to call this state 1, and I'm going to call this state 2 right there, right? And writing this thing out for the main equation for us for work energy. Let me start going down the list. Right here, it starts from rest, it's 0. The potential energy at state 1, now that's going to be all about the springs. Now, I think I want to convert my K right here into pounds per foot. Just a good practice. We have 1.6 pounds per inch. Now, I need to get that pound per foot. Now, I know that I have 12 inches per foot, right? So the inches cancel out. So that's going to get me a spring rate that's going to be useful to me right here. So I'm going to go 1.6 times 12, and I'm going to get 19.20, and that's pounds per foot. I also want to get the del that's taking place. All right, so I'm going to call this one, I guess this is going to be O, and I'm trying to think of what I decided to call this right here. I think this is going to be, this is B right here, and I'm going to call this location A right there, okay? So my del between O and, excuse me, A and B, let me start with A and B, is going to be 5, right? But I need to be it in feet. So 5 twelfths should be 0.4167 feet, right? That they told us it was going to move that amount. Now this other one, we have an unstretched is at 12 right here, but now it has just moved over here. So it has moved a certain amount. So how much did it move? Well, if you do the math right here, you find out we get a 5, 12, there's a 13, 5, 12, 13 is a standard triangle right here. So it's 13 inches long here where it was 12 over there. So it has changed. It's del, I'll call it OB, or OB, and this is state 1, I should say. It's going to be 13 minus 12, and we'll divide it by 12 right here. And so it's just going to be 1/12, right? So it's going to be 0.08333 feet. So when we come up to here, what we could do is say we have a 1/2 K, and I'm going to del, I'll say AB1 squared plus 1/2 K del OB1 squared. There's no external work. Coming to the next one. The kinetic energy is going to be equal to 1/2 mv2 squared. I don't think we need anything here. I think we could just say, I said 2. I said b in there, but it doesn't really matter. And then the potential energy at that state is going to be 0. So we're going to plug all these things in up above, along with our values right in here. So I'm going to say I have 0. I'm going to say my potential energy is going to be 1/2 19.20 times 0.4167 squared plus 1/2 19.20, and it's going to be 0.08333 squared right here, okay, plus 0. It's going to be equal to, because that, okay, so that served a placeholder for this, and it's going to be equal to 1/2. Mass of this thing is 10, so divided by 32.2 to get the mass, and then we're going to say V2 squared, and then plus 0. All right, so if you were to take all of this right here, what you would find is you would get 1.733, and these would be foot-pounds right there. By the way, if you take this right here, 0.1553, it's just useful to try to do that. And we end up with rewriting the thing out, 1.733 is equal to 0.1553 V2 squared. We find that V2 is going to be equal to 3.341 feet per second. All right. So that's going to be with the maximum speed, maybe even write max as part of that right there. So we can see that that's the max as part of the answer. Right, max. Now we want to try to get the maximum acceleration of the collar. Now we can't use a strategy where we find the velocity and then find the constant acceleration, because it's not a constant acceleration problem, because the force varies with position, right? The force here changes with where, the force is getting large of the spring is larger and then becoming to nothing when it gets over to there. The same thing true with this. So it becomes kind of hard to use those. You can't use that kinematics. You just can't do it. So what you want to do now, you need to have use kinetics, right? So we need to decide where we're going to use it. Well, where is the acceleration going to be a maximum? It's going to be a maximum right here, right? Where this is going to have the maximum velocity, so acceleration is going to be 0 right here at that spot. But the acceleration right here is going to be where the acceleration is a maximum. So what we want to do is we have to use Newton's second law for that, and use an FBD and an IBD, and see, well, what are the forces that are acting onto this right here? Well, we have a couple that we might want to put onto both. Yeah, I think we have a weight of this taking place at 5 inches compressed. Yeah. And that's something also I didn't point out right here, that this was a compressed spring and this was a stretched spring, but it didn't matter as far as the energy concern. So here's our force. We're also going to have, like, maybe I'll put over here Fn. There's going to be a normal force coming that way. But we're going to have the force of the spring, I'll call it S. I'm going to go, I think I called it BC here. I'm going to go spring 2. And then, but I'm also going to have the pull of spring 1. I'll call it spring 1. And then we're, in terms of acceleration, we're going to have mass times acceleration right there. So we're going to need to figure out what the spring forces are as part of this right here. So I guess I decided to go ahead and write the thing out here. Yeah, so in the x direction. So I said that I have a negative fs2 and then a negative fs1, but only the x component of it, which is going to turn out to be 5/13ths. Right there, right? Because we have that 5, 12, 13 triangle right here. And that's it for forces on this thing. And it's going to be mass times acceleration. And I should say that it's going to be a negative acceleration, right? It's going to be going in that away's direction. In x direction, let's say. So put in numbers in here. I need to have the force of this is going to be that displacement right here, right? So we're going to have, and actually we could actually use inches and pounds as part of this, by the way. So we're going to go negative fs2 is going to be that 1.6 times our 5 inches. Right there, right? So that'd just be pounds, right? Because you get pounds per inch times inches, we're good to go. And then this one is going to be 1.6 times 1, because it's only compressed 1 inch or stretched 1 inch, and it's 5/13ths. It's going to be equal to the negative 10. It's 10 pounds, 32.2, and we get the acceleration right there. So we're going to get an acceleration of 27.7 feet per second squared. And it's going to be in that direction right there. So we can make that into an acceleration. And I said it's in the x direction. Maybe I should get rid of the subscript x. This part here. It's like, who is texting me? CVS Pharmacy. So they're telling me that something is ready. Your order is ready. Be prepared and stay well within. Oh, that's nice of them. Okay. So there you go. Another video bites the dust. Oh, it bites already.